Good morning, all. Happy Wednesday. Almost April, which is crazy to think about. Where did March go? What happened to March? Come back. I want March back. I'm not ready for April. But it's here tomorrow. Okay, so I teach stats tomorrow. What kind of April Fool's joke should I play on statistics? What should I do? I need, if you have suggestions on good April Fool's jokes, let me know. Okay, let's do a quick little recap of what was happening on Monday. On Monday, we started looking at multiplication and division of fractions. Specifically, we spent a lot of time looking at multiplication of fractions and understanding how we can use that area model to multiply fractions that involve fraction times a whole number. So we looked at using the area model and kind of distributing objects really nicely in order to make that multiplication work. And sometimes it doesn't work out as nicely as one might hope. So we took a look at some examples where we had some leftover stuff that we had to divvy up and put into those equal sized pieces. So yeah, it could get a little messy. So if you do have to explain this concept, just kind of be mindful of how messy you want it to be. But eventually you want to be able to kind of zero in on some of these properties. And the special properties are this idea that the numerator and the denominators can get multiplied together. So that's the general rule for multiplication of fractions, which is super nice. I think that's a very nice property for multiplication of fractions. Okay, so we are going to spend a little bit of time this morning looking at division, and we're just going to maybe remember some stuff that we maybe haven't thought about in a while. All right, so bonus points this morning at 9:30, if you can remember the two models of division and how they are different from each other. That's the key. That is the key thing. If nothing else, you should know some names for the two different types of division, so that way if you get lost, you can always look it up on the internet because the internet is a good resource for these kinds of things. I call one of them the partitive model, but it's sometimes called the fair share model as well. And this is the model that we use to model the standard algorithm of division. So this is where we model the total number of groups. So we think about that divided by a number as the total number of groups, and we try to distribute stuff evenly into those groups. So this is the one where we model the groups and then try to fair share everything into those groups. So for example, if I had, let's see, if we had like 8 divided by 3, what we would do is we would model the groups. Okay, so I have 3 groups. The 8 represents the total number of objects we have. And what we're going to try to do is fair share those 8 objects into these 3 groups. And we do that just by counting up. So 1, 2, 3, 4, 5, 6. And then we get kind of stuck with 2 leftover objects that we can't distribute into 3 equal-sized groups. So the answer to this particular question would be we get 2 objects per group with a remainder of 2 objects left over that can't be distributed. So this is the partitive model. So draw your groups, distribute your objects by counting up, and then we looked at how like all these leftover objects. So our kind of goal today is to deal with the leftover objects in a fractional kind of sense. And we'll eventually talk about working with decimal numbers as well. But that's the idea of the partitive model. So you just want to fair share your objects into the equal sized groups. The other model is called the measurement model. Or I've also seen it called the repeated subtraction model. And in this model, what we do is we repeatedly subtract groups of objects until we can't subtract anymore. So let's take a look at the same division statement of 8 divided by 3 and see how that's different using the measurement model. So in the 8 divided by 3 model, we still have a total number of objects. That's, oh, I actually, can you, I need to just add something in here. So what we actually need to do is we actually need to model the total number of objects first, and then we start repeatedly subtracting. So I missed a little thing here. So you just want to insert this up top that we actually want to model the number of objects. So just slide into that DM. I mean, slide, toss that in up top in whatever way seems reasonable for your notes. And because we do have to have something to repeatedly subtract. And in our case, we're going to be drawing 8 objects and we're going to be subtracting groups of 3. So for the measurement model, it might look something like this. 1, 2, 3, 4, 5, 6. So we model our objects, and then we come along with, we can actually do this physically if we need to, but we're just going to kind of subtract away groups of 3, and then we count how many groups of 3 we have. So here's 1 group of 3, here's 2 groups of 3, and then I can't take away any more groups of 3, so I'm kind of stuck with this remainder of 2. So we end up getting 2 groups of 3 with a remainder of 2. So that's just a little recap of those 2 models. So notice that the partitive model models the groups, and then our final answer tells us how many objects there are in each group. The measurement, or the repeated subtraction model, we model the objects and we subtract equal-sized groups, and our final answer tells us how many subtractions or how many equal-sized groups we were able to get with that remainder. So they feel very similar, they just look slightly different, and students have the capacity to use one of these 2 models. These 2 models are quite flexible, as we'll be able to see here in Fractionland. So how do those feel, guys? Do you remember those? Are they slowly coming back, trickling back into the cerebellum? Great. It's true, and that brings up some. I love talking about how we learn and stuff like that. I think that's very important. Well, Connor, you bring up a really fun point, and it's scary how quickly we forget. But you have to remember that our brains are kind of set up to do that, right? Our brains are set up to forget stuff. Could you imagine if you had to walk around all day, every day, remembering every single thing that you learned from like the day you were born? You would be like so overloaded on information, it would be insane. So yeah, your brains are set up to forget some of this stuff if you don't use it, which is why you as teachers, if there's stuff that you want your students to know, you want to make sure that you repeatedly practice those kinds of things. Especially important things like multiplication tables, addition facts, those kinds of things I think are very important. And so if you actually have learned something, yeah, repetition is good, right? I mean, think about something that you're really passionate about, right? Something that you know really, really well. You probably know it really. I mean, for me, it's like it's Pokemon. I know like every Pokemon name. I know, you know, which Pokemon can attack other Pokemon because I use that information every day, right? So if you use information all the time, it's going to be very easy for you to go into your memory, find that piece of information that you need, and use it. If you don't practice stuff, I mean, I can remember the names of like hockey teams, but I don't know anybody who plays on hockey teams anymore because I don't watch hockey that much. I know how to play hockey, right? So I learned that as a kid, and I used to watch hockey with my dad all the time. So I know how to play the game, but I know nothing about current day hockey because I haven't used that information. And I say forget in kind of like a very loose sense too. Provided that you know the information very, very well, it does get stored away. It just gets harder for you to find it. So think about like a filing cabinet. So like if you learn something really, really well, so like let's like for me, like that's my multiplication facts. I've learned that really, really well. It's got stored away in a filing cabinet, and maybe I don't use it every day, but I know where to find it. It's the same thing with like long division is such a good example. If you've learned long division or the multiplication algorithm really, really well when you were in elementary school and you revisit it as an adult, it might take a little while to get back into it, but once you see a couple examples, you kind of get it, right? You can kind of go back and fish that information out from the filing cabinet. So you don't really, like if you've learned something well, you don't really forget it. It just becomes a little bit harder to find inside of your brain's filing cabinet. That's all. So that's why we want repetition, right? We want to teach our students how to do some of these things because if they do have to use it eventually as an adult, we want it to be easy for them to find. I mean, do I care that all students know how to do long division by the time they get to high school? Not really. Like I don't really care. But maybe they're going to be teachers in the future. Maybe it'll be nice for them to know how to do long division in somewhere in the future. That's kind of my philosophy on a lot of mathematics we learn. Do they need to know a lot of this stuff? Probably not. But I want to make it easy for them to find in case they do need it. Okay, now that's me talking about learning in business. If you're curious about that kind of stuff, I have done several presentations, and I'm happy to post presentations like that for you to watch at a different time. But for now, we are going to look at an example involving division of fractions because division of fractions is weird. And yeah, and we want to develop, I think, some ways to think about division of fractions. And I do find it easy to explain through the models of division. So a classic example where we see fractional thinking is in baking and measurement kinds of things. So here we have 7 halves cups of sugar, and it's going to take us 3 halves of a cup to make 1 cake. We want to use all the sugar. So maybe let's just write down here. We do want to use all the sugar. So use all sugar. And so the question is, how many cakes can we make with the 7 half cups that we have? Or I guess I could have put that into decimal form or a mixed fraction, but so I might be able to make some amount of whole cakes, and I might also be able to adjust the recipe in some way to make some kind of smaller portion of that same cake. So this happens in baking and cooking a lot, right? Where you want to half the recipe or double the recipe or something like that. So let's assume that we're going to use all the sugar. We're going to make as many cakes as possible, utilizing the same recipe. Okay, so what do we have? We are given a couple pieces of information. We are given the total number of objects that we have. So that's given up here. Okay, so we have essentially seven objects, and the objects that we're working with are half cups of sugar. Okay, so remember, I like to think about a fraction as a unit. So there's kind of like two units here, right? We have seven objects, and the units that we're working with are half of a cup, like half cups is kind of how I would say it. So that's our total number of objects. We got seven objects. And what we want to do is we want to kind of think about what this means. So it's going to take us 3 half cups in order to make 1 cake. So this is how many objects go into each group, essentially, right? So if we think about 1 cake as a group, then it's going to take 3 objects to make one of those things. Does that make sense? So this is giving us some information about the total number of objects in each equal-sized group. So see if that makes sense. So this says if we think of a cake as one of our equal-sized groups, 3 half cups must go into each group. So this tells us how many objects are going into one of these groups. Now, with that information, we should be able to scroll back and figure out which one of these division models is going to be helpful for modeling our problem. So what information is given to us? Well, I mean, we have the total number of objects. That's not a big deal. But what else do we have? Do we have the total number of groups that we want to make? Or do we have the number of objects in each group? Well, I would probably argue that a measurement model would be helpful because I don't know how many cakes I want to make. I don't know how many groups I'm going to have. So partitive model is not super helpful in this case. But the measurement model might be helpful because I have the total number of objects. I know how many objects are going to go in each group. So I should be able to subtract those equal-sized groups and hopefully figure out how many cakes we can make. So that's kind of the idea here. So this is kind of suggesting that the measurement model might be a nice way to think about this problem. So this is our discussion here. So I always try to use I like the partitive model a lot because I think it's very straightforward. But in this case, I don't think it's going to be helpful. I don't know how many groups I have, so it's going to be relatively hard to set up and execute the partitive model. So I'm going to start thinking about, okay, my other model is the measurement model. Let's try to model our 7 half cups and take away groups of 3 half cups. Okay, so let's go ahead. Let's try to set up an area model for 7 halves. And then we're going to start working on that procedure of taking away 3 halves at a time, see how many cakes we can make. And Bob will be your uncle. Okay, let's see. Let's throw some shapes down. Let's get a rectangle. Well, do you want to do circles today? I'm feeling circles. I'm kind of feeling like these are halves. Maybe we can do some circly boys today. So let's model 7 halves. Okay, I'm going to need quite a few circles probably for this. Okay, so 1. Can I, oops, no, stop. No, what's happening? Go away. Weird, it won't let me copy and paste this. Why? Why does Microsoft suck sometimes? Why? I sometimes I don't get how Microsoft is still in business, because like I literally should be able to press copy, press paste, and get a second circle and not highlight everything on my screen. So I'm going to close OneNote because it's spasming a little bit, and we'll try this again. Cool. Okay. Attempt number 2 at using the copy and paste function to be able to do something. Alrighty. So let's see. I'm going to need 1, 2, 3, 4, 5, 6. I'm going to need this copied again. Okay, wish me luck. I don't know why copying and pasting is so challenging. Okay, that should hopefully be enough. Let me just adjust some stuff so it's kind of roughly in the same neighborhood. And we're going to divide all of these in half, and we are going to do the area model for 7 halves. And I will do that in green. So here's 1 half, 2 halves, 3 halves, 4 halves, 5, 6, and 7. So there are our 7 half cups. And in red, I'm going to go ahead and I'm going to start subtracting groups of 3. I'm going to start subtracting 3 halves at a time. So our first subtraction happens here. So here is 1 cake. So those 3 half cups will make a singular cake. Here is our second group of 3 halves. Here is 2 cakes. Now be careful. What we want to think about now is how much of a cake we can make with this leftover portion. Okay, so how many portions, how many halves do I need to make a singular cake? Yeah, that's awesome, Melissa, because this is the tricky part I find with division of fractions, is you have to be mindful of what you're comparing to. So you're right, this is not going to be a half cake. This half cup can actually make 1/3 of a cake. If it takes 3 half cups to make a cake, then 1 half cup is actually 1/3 of a cake. So yeah, that's a nice little noticing there. So this is the hard part, I think, of the model. So if you can understand that, then you're golden. Then division of fractions is easy with these kind of smaller model-y scenarios. Give me one. I see your question, and I feel like that's a good question. So give me a hot second to write something down and think about that. Yeah, so I think you've noticed something here that I've done explicitly on purpose, and that is to make the denominators the same, the 7 halves and the 3 halves, so that the subtraction works really, really nicely. Yeah, so that is, I guess, the key to being able to utilize this question in a nice way is to have similar denominators so that the modeling works out really, really well. Now, we can probably do something similar if the denominator is different. It's just going to be a little bit harder to do maybe the subtraction, for example. So you can imagine if you still modeled 7 halves, but if all of a sudden it takes 3/4 of a cup, it's going to be a little harder to do your repeated subtraction. But I think we could pull it off. We can certainly look at a similar example with a different denominator after if you'd like. But what I want to do, let's finish up this one first, and then we can think about your question, because I do think it's a good question. Okay, so what we've done is we've tried to model the following division. We have tried to take 7 half cups and to divide it into essentially groups of size 3 halves. And what we found was we were able to get 2 whole cakes and 1/3 of a remaining cake. Okay, so this is what we showed visually. If I start with 7 halves and I start collecting groups of size 3 halves, we're able to make 2 whole groups plus a leftover 1/3. Okay, so the 2 represents our 2 whole cakes. And this is our remaining 1/3 of a cake. Now I do want to put this into improper forms, and hopefully when we put this into improper form, we'll see a little bit of a pattern here. So So in improper form, this should be 7/3. And this is what I want you to notice. This is something that we don't typically talk about, but I think it's interesting. And that is, most students learn that division of fractions is really like multiplying by the reciprocal, which does work. And I'll show you what I mean by that in a moment. But it's also true that division of fractions actually works the exact same way as multiplication of fractions, in the sense that I can actually just combine the numerators together with a division symbol, and I can combine the denominators together with a division symbol as well. And some students actually really appreciate seeing it this way. This is potentially maybe something new for you guys, because I certainly never learned this when I was in middle school. And if we simplify this, right-hand side over here, we get 7 divided by 3 in the numerator, and we get 2 divided by 2, which is just 1. So we really just get 7 divided by 3. And if we interpret 7 divided by 3 using a fraction bar, we do get 7/3. So I just wanted you to see that, because that is a nice property that you can utilize. Most of the time, we teach students the following. Which tends to have a little bit more benefits when thinking about algebra. So this is usually the standard way to think about division of fractions, and that is if I take the second fraction, which is 3 halves, and I make it into its reciprocal, which would be 2/3, and then multiply instead of division. So if we do this, and then we kind of go through that procedure of multiplying together the numerators, multiplying together the denominators, And maybe canceling out these common factors of 2, we end up getting our 7/3 as well. But both work. I mean, both of these methods are true and will work. I find the first one a little bit more interesting because then it's actually feels like it follows a pattern that's similar to multiplication. But this is true in general. So maybe let's just write down these two things. So in general, if we have A over B divided by C over D, we can go one of two ways. We can flip the second fraction and multiply. In which case, we're going to get A times D in the numerator and B times C in the denominator. So that's way one. This is called using the, this is called multiplication by the reciprocal. Now, way number 2 is a little unorthodox, but it is technically true. And way number 2 is just straight up using division. So in other words, what I could do is I could take A and C, which are both in the numerator. I could actually divide A and C. And then I could take B and D, which are both in the denominator, and technically divide by those things as well. So both of these are true. And it depends kind of how you want to approach the situation. I think way number 1 has a bit more impact, like I said, with regards to doing work with algebra. It's a little bit easier to multiply things when it comes to algebra, a little bit harder to divide by things when it comes to working with algebra. But way number 2 is nice if the numbers happen to be super nice. So let's maybe come back to Alyssa's thought. So now that we've kind of summarized a couple of different ways we can work on division, let's revisit that example. But instead of subtracting 3/2, let's subtract 3/4 instead. Okay, so we're going to keep our 7/2. So actually, I'm just going to probably go up and just copy and paste that because that's probably the easiest. So let's get set up with our 7/2 cups first, and we're going to subtract off 3/4 cups per cake. So hopefully you can see that this is still very doable because of the nice denominators that I've chosen here. Still very doable, but there is that extra step of having to convert the 7/2 cups into quarter cups, right? If I want to subtract 3/4, I don't have the capacity to do that right now, right? I only have halves right now. And if I want to subtract quarters, I need to divide all of this stuff up into quarters. So you would technically have this extra step of slicing everything up like so. And by converting your picture into quarters, now we have the capacity to take away 3/4 cups at a time. So that would be step one. Or could you expand the 3 halves into 6 quarters? You could. I mean, you could, but I mean, if you start with 7 halves and you're subtracting halves, in our case 3 halves, it doesn't make sense to turn it into quarters. I mean, you could, but it doesn't really make sense. So the idea is whatever this number is, whatever you're going to be subtracting, that's going to be the model you want to match up. You want those denominators to kind of match up, if that makes sense. Cool, yeah. So it's all about what you're subtracting, because, and let me just kind of finish up by starting to subtract these things, right? So you can see here that because we're subtracting in quarters instead of in halves, I need to have these portions in looking the right way. So this would be 1 cake now, right? Those 3 quarters that I've taken away from the picture. And we just can kind of keep going and doing this. So here would be our 2nd cake. And here would be our 3rd cake. Fourth cake. And then we have this leftover bit, right? That we need to figure out how much of a cake is left over. So if it takes 3/4 of a cake, 3/4 of a cup of sugar to make a cake, and I have 2/4 left, how much of a cake can I make with this leftover portion? 2/3, yeah, exactly. You got it. So if we kind of go back to that last example and switch it up a little bit, we can still utilize the model. It just becomes a little bit harder. And again, you kind of end off with this kind of awkward 2/3. I find that 2/3, that's like, it's a little bit harder, right? It's just a touch harder to kind of think about at the end here, but still doable. So let's see, we got something like this. 7 halves divided by 3/4 is equal to, how many holes? We had 1, 2, 3. We had 4 whole cakes and 2/3 of a fifth. Right. So this is there a visual step to show the last part to come up to 2/3? Not well. You could do this. So you could do this, Wakan. I think this might be helpful. So let's pretend, let's pretend that I had another third, and I go and I circle, what I would subtract. Right, so this would be a whole cake, right? But I only have 2/3 of that cake shaded in. So yeah, you could pretend, you could circle another cake and be like, well, I don't really have enough to make a full cake, but I'm 2/3 of the way there. Yeah, so I think that might be the easiest way to do it. And then, of course, there's nothing here, so we don't care about that empty quarter here because there's nothing in there, so we don't care about that. So yeah, hopefully that helps and makes sense. But what I want to really focus on is, let's convert this to an improper fraction and look at those two more algebraic approaches to division. So if we convert this into an improper kind of fraction, this would be 12/14 thirds. 12, yeah, 14. Okay, so I think either one of these final answers is fine. I think based on the picture model we have, the first one makes the most sense because I can just count how many holes I have, and then I can tack on that remaining 2/3 of a cake. I think that makes sense. But for the sake of trying to connect this to a more algebraic kind of thing, this one's helpful because now we can come back and we can go, okay, 7 halves divided by 3/4. How do I want to approach this problem? Way 1 says we could leave the first fraction the same. So this is way 1. We could then multiply by the reciprocal of the second fraction, and then go through the procedure that we know how to do for multiplication. So I know that now I can just multiply the numerators together. I can multiply the denominators together. and get a fraction and maybe try to simplify. I like simplifying along the way. So my preference might be to do something like this to try to get rid of that factor of 2. And then I get 7 times 2 for 14 in the numerator. And I essentially get 1 times 3 in the denominator for 14 thirds. So that's way number 1. This is, like I said, the usual or the standard approach to thinking about division of fractions. Way 2, I find to be a little bit more interesting because this way you can kind of follow the nice pattern of if you got multiplication, just multiply the numerators. If you got division, just divide the numerators. So don't know if it's going to be super helpful in this particular example, but let's try anyway. Doesn't look like it's super helpful. So, I mean, we could start interpreting some of these division symbols, like 7/3 isn't super helpful, right? So maybe what I'll do is I'll kind of convert 7/3 into something like this. Right, so convert that division into a fraction bar so that I can actually maybe do a little bit of work here. And then in the denominator, we have 2 divided by 4. Again, not super helpful. I mean, maybe we could make that 1/2, right? 2 divided by 4. Maybe we could make that 1/2. So I think you're still kind of going to get stuck and you're still going to have to do a multiplication, right? I think that's still eventually going to have to happen for way number 2. But it will eventually get us to 14 thirds. So we can kind of struggle through converting divisions into fraction bars and so on and so on. But I think eventually you're still going to have to use the reciprocal to multiply. I don't think you can really get around. I don't think there's a nice way to get around not having to use this concept of multiplying by the reciprocal. So let me just, I'm going to play a little bit. Yeah, I don't think there's an easy way to get around it. So I guess when it comes down to kind of thinking about fractions, way 1 is the most beneficial because it's the most flexible. Way number 2 is nice if A and C are nice numbers and B and D are nice numbers. So I'll show you an example of where way number 2 is maybe a little bit more helpful. But if you notice that the divisions are really, really nice, it's really easy to utilize the way number 2. But way number 1, I think, is the one that's gonna win because I think it just has the most use cases. It's the most beneficial overall to know that procedure. So this was just me kind of playing around and seeing what I could come up with the 2 different ways. So way 2, super not helpful. Way 1, probably more helpful than way 2. Okay, let's look at an example using the partitive model too, because you could have word problems designed to utilize the other model as well. So let's see. So here would be an example of the partitive model. So if we have 7 half cups of sugar again, so that's going to be our total number of cups of sugar we have. And we want to use all the sugar to make 2 equal sized cakes, essentially. So we want to divide this into 2 equal sized groups. How much sugar goes into each cake? So once again, I'm just going to go back and I'm just going to kind of highlight some of the information here. And I'm just going to write down some stuff in a different color so you can see how this is just slightly different from the last kind of example. So again, we do have our total number of objects. Okay, so 7 half cups is going to be our total number of objects. But in this case, we're given the total number of groups that we want to make. And so our goal essentially is to try to figure out how many objects go into these two equal-sized groups. So that's what it feels like to me. I'm given the total number of objects, I'm given how many equal-sized groups I need, and I want to fair share the half cups into those two groups. So the partitive model feels like it makes sense here. So what we're going to do first is we're going to model the total number of groups that we have, and then we're going to start fair sharing our half cups into those groups. Now, here's where it's nice to have some of your fraction manipulatives that we talked a little bit about on Monday, because I can actually model using some of those fraction manipulatives, and then it's easy to kind of pick the half cups up from that model and move them into the groups. But for now, let's just go ahead. We're going to model our groups. And over on the side in red, I'm just going to model the half cup. So I'm going to decide to use rectangles here. So this is our area model representing 7 halves, or I like to think about it as 7 of something. So this is 7 half cups. Because I really just have 7 objects, right? Like it's just looks a little, like I still have 7 things. Hopefully that makes sense. I still have 7 things. I got to move those 7 things into these 2 groups. How many of those things are going to go into each group? Well, we can just start counting. There's 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves. And so maybe what we want to do, maybe you want to kind of group these things together. So, maybe it makes sense to move some of the whole regions. It's totally up to your preference, how you want to go about teaching this. But yeah, you could technically kind of fair share the whole portions first. So I could, for example, take this whole portion, put it over here, then take this whole portion, put it here. And then we have this thing that can get divided into halves. And then we have this leftover thing down here. So it really is kind of up to you. Do you want to fair share the whole portions? Do you want to just kind of count along and be like 1, 2, 3, 4, 5, 6, 7? But either way we go about doing this, we should end up getting one whole portion and a half in each one of these circles. But I mean, personally, for me, if all of these things over on the right-hand side break apart, and I can literally just count by halves, I'm probably going to end up with, they kind of look like faces. It's making me weird. But we should end up with 3 halves, essentially, in each one of these groups. Okay, so now the question becomes, instead of interpreting the leftover as a part of the cake, I actually need to distribute this leftover thing into our 2 cakes somehow. So I have 3 half cups in each cake, right, just by kind of fair sharing, but we have this leftover half cup that needs to get divided into 2 equal-sized parts. So how much extra is going to be going into one of these groups? So let's just take a moment. Let's pretend we've fair shared all 6 of those halves. But I have this leftover half cup, and I need to be able to fair share it. And yeah, we want to show that an extra quarter is going to end up getting put into each one of these cakes. So if I come back up here and I look at this area model, what we could do is we could divide the half, the remaining half, into 2 equal-sized parts. And by doing that, we see that now it becomes a quarter of the original whole portion. So this remaining 1/2 that's left over after we divide it is going to actually add an extra 1/4 to each cake. Okay, so in other words, at the end of the day, each cake is going to have 3 half cups of sugar plus this leftover 1/4 cup based on that half that we just weren't able to distribute nicely into 2 equal-sized parts. Okay, so now we should be able to make a division statement here. We should be able to say something like 7 halves divided into 2 equal-sized groups is 3 half cups plus a leftover 1/4 cup. So let's add the right-hand side and actually see what happens. And let's see if we can kind of interpret this division. So let's go ahead, let's add these 2 fractions together. We can do that by finding a common denominator. So let's multiply our numerator and denominator by 2. And we see we get 6 plus 1/4. So we have 6 quarters plus another quarter. That should give us 7 quarters altogether. And if you want this as a mixed number instead of an improper fraction, that would be 1 whole piece and 3 quarters. And you can go back to the model if you want and play around a little bit. You should be able to show that you get one whole portion plus a leftover 3/4. But hopefully there was enough explanation here to kind of show you how we would set this up as potentially as an addition of two fractions. Okay, so what we want to now kind of think about is, does this turning into this still follow the same rule that we looked at before? So can I still interpret this division as like a multiplication by the reciprocal? Does that still work? Now, this is where it's helpful to be able to think about a whole number as actually being divided by the number 1. So this whole number 2, we can actually think about it as 2 divided by 1. So this is an alternate representation for the number 2. And that allows us now to multiply by the reciprocal. So now I can take my 7/2, I can change my sign to a multiplication sign and multiply by the reciprocal of that second fraction. And we see that by doing that and multiplying our numerators and denominators together, we do end up with the 7/4 answer that we got from looking at the model. So everything does kind of connect back to that generalized rule of understanding that we can change a division to multiplying by the reciprocal. Okay, so I think for the last couple of minutes, let's try a few more examples. So let's try modeling the following examples using measurement division. I'm just going to make some stuff up, so hopefully it works. Let's take 9/5, and let's divide that into groups of 2/5. And then we'll do one that's maybe a little bit harder. I think those will be good. So we're going to actually draw a full picture for this one. I hope that if you are at the college level, you would know how to multiply by the reciprocal and find the final answer. Of course, you can kind of pre-check to know what your final answer should be. So for example, I know up here that this is going to be 9/5 times 5/2. I know that my final answer is going to be 9/2. Right, so you can check. This is kind of our goal. Our goal is to show that the picture model actually does give us 9/2. So I'm going to just maybe toss that over on the side. So we want to show that this one is going to come out to be 9/2. And what's this one? 11/4 times, this would be times 2/1. So this one should come out to be 11/2. Okay, so we have some kind of idea of what our final answer should look like. So I think that's helpful, right? Knowing how to do this procedure is going to be helpful for you as a teacher to know what that model should look like. So let's see if we can actually do it. So with measurement division, we want to model the total number of objects and then repeatedly subtract the second fraction. So we need to model 9/5. We're working with fifths here, so maybe I'm going to go with some rectangles, and I'm going to need 2 of them. Okay, let's divide this into 5 equal sized parts. 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to shade it in green. So 1, 2, 3, 4, 5, 6, 7. So here it is. Here's our 9/5. And in red, I'm going to go through and I'm going to subtract off groups of 2/5. So here is a group of 2/5, for example. Here is another group of 2/5, and so on and so on. Now, if we kind of come back to Wakana's original kind of question, which was, is there a visualization to show how much this should be, this leftover part should be? And it's, okay, if I want to show that visually, I'm going to pretend that I can subtract off another group. But notice that it's really only 1/2 of this leftover group. So now we're going to go back and we're going to count how many times we were able to subtract off groups of 2/5. 1, 2, 3. We were able to get 4 groups of 2/5 plus 1/2 of a group. Okay. Our division statement then becomes 9/5 divided by 2/5 is equal to 4 whole groups plus a leftover 1/2 group. And you can see if you convert that into a mixed number, we get 8 plus 1, which is 9/2. So that's our picture model for the first question. So those are nice kind of introductory questions because they're using similar denominators. So I find similar denominators are helpful here. They're confusing enough, right? Dealing with that extra 1/2 group at the end is hard enough. So how does the picture change when those denominators look different? Goodness me, this is going to be toughy. We need to first model 11/4, and then we're going to try to subtract off halves. So since this is fourths and halves, let's maybe use circles. I think that's going to make this nice. So we need 1, 2, 3 circles. Should do the trick. And let's divide that circles into quarters. And we need 11. 1, 2, 3, 4, 5, 6. Beautiful. So here's our area model for 11/4. And we need to take away halves. So we need to remove halves at a time. This one's not too bad because I can actually see a 1/2 right here, right? So 1/2 is 2/4. So there's one group. There's one of our halves. So let's keep removing halves. Here's another 1/2. Okay, and our last subtraction would be this one here. And so we see we get a leftover. I'm saying 1/2 a lot. We get a leftover 1/2. But how many groups were we able to take away? 1, 2, 3, 4. We were able to take 5 groups away plus 1/2 of a group. Okay, so let's see if that is equal to 11/2 or not. So writing down our division statement, 11/4 divided by 1/2. What did we get? We got 5 groups. We were able to subtract 5 times, and we got a leftover 1/2 of a group. So 5 and 1/2. And if we write that as an improper fraction, we do get 5/2 is 10/2 plus 1 for 11/2. So that one checks out as well. Okay, so that's how we kind of connect that visual model to the actual process of dividing. Let's do a couple more examples here using the alternate model type, which is the partitive division model type. Let's see. Let's take Let's take 13 half cups and make 5 cakes. Well, it should work. Notice here I'm being very picky about the number that I'm dividing by. So I'm dividing purposely here by a whole number because I need to be able to model the number of groups. So the partitive model relies on this idea that I can actually model the groups. And if I'm dividing by a fraction, it doesn't really make sense to like draw half of a group. So we can really only utilize the partitive model when we're dividing by a whole number. So that's maybe something to be mindful of. We would have to use the measurement model if we were dividing by a fraction. Okay, so that's maybe something that you should note in your notes. So partitive model is good for dividing by a whole number. Measurement model is probably going to get used if we divide by a fraction. All right, but either way, what we're going to do is we're going to start by modeling our groups. So 1, 2, 3, 4, 5 equal-sized groups here. And then we're going to use the area model to model our 13 halves. And I tend to use rectangles to do this. So it's going to be 2, 4, 6, 8, 10, 12, 13. Let's break these all up into halves. Now, what I want you to think about, normally we would have manipulatives in front of us and we would be able to break these fractions like apart and move the fractional portions around. So pretend that these rectangles are kind of built together. They're kind of maybe stuck together with a magnet, but I can kind of break them apart and then move these individual pieces. So I really have 13 objects. It just so happens that 13 of those, they happen to be half-size objects. But I still have 13 things. So the idea is I can still move these things like I normally would for partitive division. I have 5 groups and I can just start counting up to 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oof, this one's going to get really interesting. I hope you are ready. Okay, goodness me, this is going to be tough. Okay, so I'm able to get, essentially, I'm able to get a whole portion into each one of these equal size groups. I'm able to get 2 halves into each group, and I'm left over with 3 halves. All right, this could get fun. But each of these little halves, so let's pretend that we're going to zoom in and kind of look at these things like so. And maybe I'll put these 2 together. So here are, this is 3 halves that we have left over. So these 3 things we couldn't distribute into our 5 equal-sized groups. So now what we have to do is try to think about how we could break these apart. And it would be really helpful to be able to break these apart into 5 equivalent pieces, if that makes sense. So kind of the idea is we would use our manipulatives to try to break these down into smaller portions. that have a similar kind of size. So ideally what we're going to be doing is kind of going 1, 2, 3. We're going to be breaking these down 2, 3, 4 into 5 smaller bits, and then distributing those smaller pieces to our picture. So this one's actually pretty hard. I probably would not want to model something like this with my students, but each one of these things now is 1/10. All right, so if I take my original whole, break it up into tenths, I should now be able to distribute those tenths nicely to each of these groups. So I'm going to represent one of these tenths by a little stick. So now I can say, well, how many do I have? I have 15 tenths. Okay, and I can just count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Again, it looks kind of like a creepy Jason face. What can we do? So this one's a little bit harder, I think, to kind of conceptualize visually because I chose not particularly nice numbers. But it's there. I mean, we take our 3 halves that's left over. We have to kind of convert that into a denominator that makes sense. And the denominator that makes sense here is tenths. And that allows us to evenly distribute the leftover stuff. And we're able to get 3/10 into those 5 equal-sized groups. So let's do a little summary. We had 13 halves divided into 5 equal-sized groups, gave us 2 halves plus 3/10. Okay, so in each equal-sized group, we had 2 halves that we were able to get, or a whole essentially, plus 3/10. And if you wanted to, because two halves is a whole, we could really just kind of finish this off and say this is 1 whole portion plus 3/10. But if you wanted this as a improper, this would be, I believe, 13/10 altogether. Okay, apologies for making that one so challenging. This is what happens when you start to make up examples without kind of thinking about what they're going to look like. It has potential to get a little messy, and this one I think got a little messy on us. But if you're able to follow along, then that's great. I mean, that's really probably one of the harder kinds of models that I would ever want to show you. I would never want to show this to my students. I think this would be very confusing for middle school students, potentially, right? Unless I explained it really, really well. Okay, let's do this last one here. 3 groups, 1, 2, 3, and we want to model 11 quarters. So I'm going to go ahead and I'm just going to draw some rectangles down here at the bottom. Maybe I'll draw, maybe I'll use squares, so it's easy to divide those squares into quarters. Okay, there are our 11 quarters. And again, I kind of think about these things kind of being put together. Think about like a chocolate bar maybe, right? So each of them has 4 pieces. I can kind of snap apart those 4 pieces. So I really have 11 separate objects, and I'm just going to start fair sharing those 11 objects into our 3 groups. So we're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're able to get 3 quarters into each of our groups, but we're going to be left over with 2 quarters. What I really would like to be able to do is fair share this stuff into threes, essentially. So let's kind of blow up these leftover 2 quarters. And divide them into 3 equal-sized pieces. So 1, 2, 1, 2. So we're going to break these apart into equal-sized pieces. Actually, it might be helpful to have a larger size picture here for you. So here it is. Here's that full whole. And I've divided my 2/4 into equal sized pieces that I should be able to divide into these 3 groups nicely. So this is the challenging part of the partitive division model, is dealing with the leftover stuff. Okay, that looks like, if I look at my whole portion, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 equal sized pieces. So I need to get to a denominator of 12. That's going to allow me to distribute nicely into these 3 groups. 2/4 is the same thing as 6/12. So each one of these little sticks that I put in is going to now represent a singular 12th. So again, this is another kind of challenging problem to think about. 1, 2, 3, 4, 5, and 6. So we're able to distribute 2 of those 12ths into each of our equal sized groups. So 11/4 divided by 3. What did we get? We got 3/4 originally, and then we had to divide into 12ths, and then we're able to get 2 12ths into those equal sized groups. So again, a little bit higher thinking than what I want, maybe a grade 6 student to be able to accomplish. Well, I mean, they should be able to do this. They're in grade 6, but probably more than what they need to do based on what the curriculum documents are going to say. This is pretty challenging to be able to kind of break stuff up like this and redistribute. But you guys should be comfortable being able to do this, I think. This is a challenge, like I said, a very challenging kind of question. Okay. Last step here is to maybe just get this as a common denominator, finish up this addition. And we see that we have 11 12ths altogether. And so what's the point of doing this kind of partitive division model? The point is to connect these numbers together. Okay, so the denominator of your new fraction that you get, your final answer, is actually equivalent to the multiplication of, this 12 is equivalent to the multiplication of the 3 and the 4, and the 10 is equivalent to the multiplication of the 2 and the 5. So that's really the key idea here, is you want to connect this to the following kind of thing, right? And show that that's really the connection with our partitive model, is just being able to flip that second number, multiply by the reciprocal, and quickly get to that final answer without having to work our way through this kind of model. That's the pattern. Yeah, that's the hard part, Vincent. So you have to look at your whole portion and essentially figure out a nice numerator. So if I look at 3/2, for example, I know I need to distribute that equally into 5 groups. So when I'm looking at this number 3, it's going to be helpful for us to multiply this by 5, because there are 5 equal sized groups. So by multiplying by 5/5, I can create a new fractional thing that I can distribute nicely into groups of 5. And a similar thing happens over here. So if I have 2/4, and I want to distribute that into 3 groups, that's kind of hard. But if I kind of multiply by 3/3, that's going to be helpful. Now I'm going to be able to get a number that will evenly distribute into the number of groups that I have. Yeah, and so like I said, that's the hard part, I think, of the partitive model. So I guess to answer your question, you multiply by how many groups there are. You create an equivalent fraction by multiplying by how many groups there are. Cool. So that's everything I want to show you guys for today. Have a lovely Easter weekend. Remember, so no class Friday, no class Monday. I will see you this time next week on Wednesday. Please make sure that you finish up your assessment, that third assessment on Moodle at some point today, so that I can mark that over the weekend. I will stick around for you, Akana, and we can chat about that lesson plan. But anyone else, have a great Easter weekend, and I'll catch up with you next week.